Next slide, Michael. Okay, hello and welcome to the Sentinel Innovation and Methods Seminar Series. My name is Rishi Desai. I'm an associate professor of medicine at Harvard Medical School and epidemiologist in the Division of Pharmacoepi and Economics at Brigham and Women's Hospital. I will be moderating today's session. The US FDA Sentinel system helps address questions related to the safety and effectiveness of marketed medical products. The Innovation Center focuses on developing innovative methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities. The Operations Center focuses on supporting the FDA in use of Sentinel Common Data Model and associated modular programs to gather evidence to support regulatory decision-making. We launched this webinar series to engage with experts and innovators in key areas related to Sentinel's master plan and Operations Center's methods work. With that, I'm pleased to introduce today's speaker, Dr. Michael Matheny. Dr. Matheny is a professor in the Department of Biomedical Informatics, Medicine, and Biostatistics at the Vanderbilt University Medical Center. He's a practicing general internist and clinical informatician, and he directs the Center for Improving the Public's Health through Informatics. Dr. Matheny is an elected fellow to the American College of Physicians and the American College of Medical Informatics and an elected member of the American Society for Clinical Investigation. His research focuses on medical product post-marketing surveillance, supervised machine learnings, and artificial intelligence-supported tool development and natural language processing. His presentation today is on opportunities and challenges in the use of large language models for post-marketing surveillance of medical products. So regardless of what types of conversations that we are having, it's impossible to avoid discussions around large language models nowadays. So this topic is highly timely and highly relevant to many of the activities that are ongoing in Sentinel's Innovation Center. So I am really thankful to Michael for sharing his insight. Before we get started, though, I'd like to mention that your lines are muted, but if you would like to pose a question as Michael is presenting, please type them in the Zoom Q&A feature, and we will get to all the questions at the end. Finally, this session is being recorded and will be made available through our webpage, which is sentinelinitiative.org. So without further ado, I will hand it over to Dr. Matheny and thank him so much for joining us. Michael, the floor is all yours.
Oh, thank you so much for the kind introduction, and it's exciting to be here. You know, this presentation is a little bit of a different flavor for me. Rishi and Sebastian had asked that I come and give a talk that really is relevant to an editorial that the Sentinel Innovation Center group has been putting together, looking at opportunities and challenges for large language models. So this is going to be a little bit more like a lecture or a general overview and less like a research topic where the individual is delving deeply into their own work. So it's going to be a little bit more survey. So hang in there with me and feel free to ask questions as you go along. So no conflicts of interest in any of the materials discussed today. All the funding I receive is either through the FDA, the VA, or NIH from a variety of sources. And this work is funded as part of the Sentinel Innovation Center under the U01 as noted from the FDA here. And so review to many of you, but what is Sentinel? So Sentinel was originally passed as part of a public law in the 110th Congress in 2007, really to establish a post-market risk identification and analysis system. And so if you look at sort of the evolution of the Sentinel system over the course of the years, as you can see on the timeline here, essentially it was established in 2007. It was launched as a mini Sentinel system, evolved under a number of years, expanding operational capacity and analytics. And then in 2016, they sort of started to think about sort of building out additional innovation centers and community outreach centers, which were funded in 2019 in order to explore additional opportunities, both to outreach and marketing for the communication center, but also to basically evaluate capacity for electronic health records and other observational, in addition to the claims data that were the anchoring foundation for the Sentinel system. And so it's a very broad base of sites and organizations that participate in the Sentinel system, listed here on the left, covers about 463 million lives, 112 million members, And it's a very large scale system with 19.7 billion pharmacy dispenses that's available for use for analytics in this network. So one of the things that makes Sentinel unique is really a focus around supporting the FDA in its mission to do ARIA sufficiency, which is active risk identification and analysis. And essentially, when you have a serious safety concern that either comes through the adverse event reporting system or through industry or through healthcare systems, there's an evaluation that then takes place in the observational data to basically assess whether or not the data available are sufficient for the analysis that needs to be done relative to the exposures from the medications and the outcomes of interest and the risk adjustment necessary to conduct this. And so if the observational data on hand is available and sufficient for the task, then there's a design and an analytic system that's put together and distributed to the Sentinel network for execution. However, if there's not a sufficient amount of data to be able to do this in a reliable manner, then these can actually sort of be spun out into other activities. But I'm not going to go into too much detail on those. What I really want to focus on more is what is causing this insufficiency. And so this is work that Judy Morrow did with a larger group that was recently published, which basically shows, if you look at the overall evaluations for ARIA sufficiency in the FDA, and you break those down into a couple of different buckets, essentially what you see is in the post-marketing space, which is the space of interest for most of the network, you can see that about a third of these ended up being insufficient for ARIA on the post-market space. And then if you look on the pre-market, that about 2/3 ended up being insufficient for a variety of different reasons related to outcome ascertainment, covariates, exposures, and study populations. So another way to look at that is if you look at this sort of reasons for the determination of insufficiency, what you'll find going more in depth into the reasons for those is that essentially the most common reason is insufficient supplemental structured data that are not available in the Sentinel Common Data Model that potentially could be available through other extraction capacities. And then sort of some other categories in terms of validated code algorithms and phenotypes and other sorts of things, along with sort of the absent terminology and code mappings. And so some of these areas are areas in which, as you'll see in the talk as we go down, that introduction of electronic health record integration with claims data and leveraging machine learning for natural language processing extraction and other sorts of feature identification may be useful in addressing some of these gaps. And so the Sentinel Innovation Center was founded in order to be able to explore some of these issues in extraction of electronic health record data from a variety of different features. So I'm trying to expand the data infrastructure to allow at least 10 million patients that have linked EHR and claims data that allows sort of large scale use of EHR data, feature engineering, which are used to explore various natural language processing and machine learning methods to extract computational phenotypes, outcomes, other exposures and risk factors, and then research around causal inference and detection analytics. So what we'll be talking a lot about today is, in fact, the top right box of this grid. And so for the last 4 or 5 years, we've been engaged in a variety of different activities to sort of explore different pieces of this information extraction and representation space. And so how does machine learning and AI play into this? And I thought I would actually just take us sort of out into a large meta frame before taking us down into the discussion around large language models. And so, I know that AI has been in a boom for the last 5 or 10 years, but really the journey started surprisingly almost 70 years ago with the first expert systems and then the first neural representation, the perceptron, that basically generated an excitement around the use of machine learning, basically use of data to learn and make inference. However, the computational infrastructure during that early period was really insufficient to the math that was being developed. And so you ended up with a lack of being able to implement a lot of these things. You ended up with a decrease. In fact, there was such a sort of a disillusionment of that discipline that AI as a sort of a term was put away, and the use of machine learning was dominated the discussion around these technologies for a number. And then, although I won't go into detail, there have been multiple other rises and falls over the years as essentially other technology stacks get developed, and then for various challenges are unable to meet the majority of the demand. So what I think stands apart for this this genre, this last decade, is that I think the technology and the computational infrastructure and the innovations in data science are actually able to achieve successes. I mean, I think there's still going to be a lot of missteps and a lot of errors, but I think that we're seeing a maturity in the discipline and in the space that will allow some things to be done that were not able to be done before. And so there's a lot of different applications of this. So you've got clinical decision support, ambient AI, imaging, processing, drug discovery. And so many of these are outside of the scope of medical post-market surveillance. But I think what makes this AI sort of time period different than the last is that we're seeing successes and diffusion of these sorts of technologies across many, many different application domains, not just in healthcare. And so this was, so I've been tracking sort of hype in emerging technologies and artificial intelligence, machine learning for a number of years. What I find this really fascinating is, so if you look back 5 years ago in 2019, and you look at sort of what was hot in emerging technologies, what you see on the list is deep learning, machine learning, and natural language processing as an entity. And what NLP was in 2019 was essentially the use of machine learning to basically process documents and then assess control terminology terms across a document in order to be able to use those. And so what you see when you fast forward just 4 years into 2023 is that all three of those are actually no longer on the cycle. They've been largely supplanted with generative AI and a focus around large language models as a way to sort of analyze and evaluate and interpret natural language. So there's a lot of different things that you can do with large language models. I think, you know, as a clinician, I'm a primary care clinician, and I'm really excited about the opportunity for ambient dictation to be able to sort of listen in on a clinical encounter and generate a draft of a note for me to be able to use. I think there's opportunities for clinical summarization to reduce cognitive load, and then for patients to basically adapt the medical language and the medical results for their individual learning and care goals and reading levels. Tons of opportunity in this space. So I want to take the global AI timeline and sort of adapt that down to the topic at hand, which are large language models. As long as the field has been 55 to 2024, if you look at the key technologies that basically LLMs are standing on, pretty much all of them have been developed since 1995. And so well, I'll be talking briefly about long short-term memory, about vanishing gradient, word-to-vec, transformer solutions. But if you look at that, you basically have a span of 10 years of innovation that has essentially created the foundation for what we now know are large language models. And then if you look at large language models themselves, you can see a very, very rapid expansion and evolution of the different implementations of large language models. And so I think that one of the key take homes for one of these foundational technologies along short-term memory is, you know, the old neural networks that were present, really present from the 70s and 80s. The key innovation here is that they basically found a way to allow some information that the model was learning to be retained and to be sort of retained in the weights, and actually allow other information to be forgotten or discarded over time. And so what this allowed it to do is basically be able to sort of integrate sort of longer term information longitudinally. One of the challenges, though, with this technology is that it still sort of had a limitation in extremely large chain information, such as you would find in a very long document. Sort of another key innovation in this space that sort of builds up to large language models are word to vec. And so when you think about sort of a feature space of documents and words, sort of an old representation of that might be a sort of zeros and ones, where each possible word in a document could be a zero or one. And so what you end up with is this insanely large matrix of sparse matrix of zeros and ones for each of the different tokens. And what Word2Vec did was they basically used an embedding layer and a couple of different pieces to transform that large sort of sparse data model into a continuous vector that actually had a mathematical representation such that the distance between these vectors would generally relate to terms. So if you look on the right here, you have, man has a relationship to woman, and there's a sort of a distance in the multi-dimensional space that the vectors represent, such that you can actually use those representations to help make comparisons, make analogies. And it also drastically increased the computational efficiency of using these types of methods. Probably the next innovation that I think really sort of drove LLMs are two things. One is the transformer model, but underneath it is sort of a concept that that instead of just evaluating sort of one sentence at a time or one word at a time, which the older LLM technology or the older natural language processing technologies did, transformers essentially allowed the entire document or entire corpus to be analyzed, put into vectors, and sort of assessed at one time. So previously, you would have had like a word or a sentence in the first paragraph, and then 10 paragraphs down, you would have had a different word or a sentence. And there was no way for some of the older NLP technologies to actually sort of correlate those or align those, even though they might be really, really relevant and important to each other. And this translation or this transformation of an architecture allowed that to be possible. And so finally, when you stack those sort of key innovations on top, you have large language models, which essentially have two key innovations. So there's an attention piece, and then there's also sort of an auto encoder piece for the text. So first, let's go through the attention. So what attention did in the transformer models, as well as the large language models, is essentially allowed you to sort of focus on certain information, retain that, realize that it's more important, and then sort of allow other information to sort of fade away. It's sort of an extension of the long short-term memory framework that we talked about before, but what it did differently is it allowed sort of much longer chains of information to go together. The other key piece of large language models is that it essentially used the decoder part of the transformer, which has sort of basically translating text into a sort of a large matrix and then decoding that back out to text. It leveraged that in order to say, well, given that I have a string of words, what is the next word that makes the most sense given the string? And then what's the next word? And then what's the next word? And then what's the next word? And then you have these amazing emergent properties where it basically generates responses and summaries and information, all based on prompts and sort of starting information relative in the training set. The beauty of it is that it's highly effective. The challenge of it is that since it's sort of an emergent property from an underlying mathematical model, and we still don't fully understand how it's able to do so well with that sort of mathematical structure, it limits us sometimes in knowing how to fix some of the problems that we'll be talking about in a few minutes. So there's also a tremendous growth in the diversity of LLM. So just in the last, I think, 4 years, you have increasingly large sort of parameters of these LLMs. So these are the number of parameters that they store as they're basically taking in large training corpora and learning from them. And so you have sort of the Chat GPT, you've got the open source technologies such as Llama and Mistral, and then you also have some of the sort of transformer technologies that are sort of the smaller LLMs like BERT, BioBERT, PubMed, BERT, that are technically more transformer based than some of the LLM word sequence. And then you've got MedPalm and SlandPalm that are essentially even larger sort of med-based transformations and large language model learning. And so how do you use these things? So there's been a lot of discussion around some of the possibilities and potential opportunities, but I think it's important to sort of talk about a few sort of base functions. So when people are talking to you about zero-shot learning, what they're essentially saying is you've got a large language model, you've built it on, millions and billions of text elements. It's sort of learned the best way to sort of predict the next word on the basis of prior words. And then you can basically give it a prompt, give it a question, and it uses that prompt to sort of uses the model to sort of fill out an answer. Zero shot means you have the model and then you start asking it questions and you get your answers. But we found in some processes that essentially the default models don't really perform as well as you would like. And so when you hear someone talking about few shot learning, what they're basically saying is we have a large language model that's sort of built on a huge volume of corpora. And what we're going to do is essentially update it with a set of labels and small sets of annotated labels in order to help sort of train it and guide it to be better at a specific subtask. And this can be image recognition. This can be, avoiding inappropriate and slur sort of language. This can be targeted towards a certain medical domain. But essentially, those are sort of common sort of concepts that are used frequently when we're talking about these sort of technologies. Another thing that I think is really exciting, and I think is going to get a lot more use in the medical field in the next couple of years, is something called retrieval augmented generation. And so essentially, again, the technology that was largely not present before the GPT, I think 2 in 2020. But essentially, what you do is you say, well, you have a large language model. And you're asking it questions, but you notice that it's not performing as well as you would like. It's not giving you the answers that you want. What you can actually do is take a set of documents. You can parse those documents using word embedding or sort of a transformer language itself. You store those vectors in a database, and then when you're asking a question of the language model actually knows what it's going to say, but then it goes to those documents and looks for basically the question that you asked. It looks for documents in that store that are relevant to the question. And then it basically creates a result that is combined from the information from the base model, along with basically pulling direct answers from the text. And in this way, you can have some really cool and interesting results from that sort of architectural framework. I'm going to talk about those on the next slide. So this is a good example of what happens when you use retrieval augmented generation and when you don't. So an example might be a user asks a question, and without sort of a RAG, basically the large language model says, well, I don't have any information on future events. I have no way to sort of know. Whereas if you actually attached it to a database, it would say, oh, based on the information in this database, I'm able to sort of give you this information now that I wasn't able to before. You can imagine for medical applications that essentially hooking it into a patient's chart as the data store would basically allow you to answer specific questions on that data store. And so some of the recent LLMs. So the other sort of angle is that there's a lot of concern that large language models that are built on large sort of public corpora, may have a certain level of hallucinations or other sorts of challenges that maybe medically trained large language models don't have, that are mainly trained on medical data. And so there's a number of those present. There's sort of Gatortron from the University of Florida and MedPalm and MedPalm 2. And so there's a lot of evaluation and interest and focus on using large language models trained from primarily medical text as well. So we're sort of taking you from the very high level to some of the just like a very brief overview of some of the key technologies for large language models. And now it's time to sort of get to the heart of the matter, which is, why does that matter to us, those of us that are really interested in post-market surveillance and medical product safety? And so really there's a sort of a growing awareness of the need for sort of careful and ethical AI. I think the presidential executive order of October 23 goes into a number of different facets around the sort of the safe and effective and equitable use of AI. But one of the things that it also called out was really the challenge to sort of bring AI in to effectively support real-world evidence, population health, and public health, of which Sentinel is one of the core parts of that. And so if you start thinking about some of the key opportunities in this space from a lens of, we have a new technology, large language models, what might this technology allow us to do that we couldn't do before. And so as part of the editorial that we put together, we sort of thought of sort of 4 key conceptual areas that particularly were amenable that LLMs may be able to support. So one is information synthesis, which is essentially taking a group of information from adverse events, from medical corpora, and basically synthesizing that information into a summary relevant to the analysis at hand. There's concept extraction, which has been around for a long time. The more UMLS based, machine learning based large natural language processing tools have been working on this for a long time, but LLMs also have an opportunity to sort of expand sort of this using a variety of different technologies to sort of expand these. And so then there's also an opportunity to do probabilistic phenotyping with LLMs and doing knowledge generation. Essentially, if you're interested in adverse events and you don't even know what you don't know, then it's possible that large-scale use of LLMs may be able to actually extract relevant information that may warrant further evaluation for downstream. And so these are some of the data sources that we are interested in when we sort of put this when we put these together. These are sort of the common pieces. I want to dive right into a really relevant example, which is this is a group that sort of put together a large language model specifically looking for adverse event surveillance around basically a flu. And so what you see here is interesting. So, I've talked to you a little bit about sort of using a large language model with, 0-shot learning, with few-shot learning. We've talked about retrieval augmented generation. And so what this group did was they essentially took the adverse event database. They annotated it in order to sort of get labels, right? So we talked about a base model, which would be in this case GPT-2 or GPT and Llama 2. And they basically used the adverse event database. They manually annotated it, they labeled it, and then they basically updated the base large language model using these annotations. And then they asked a series of prompts about it and predicted it. And then they had a reference standard that they manually reviewed in order to assess it. And if you look on the right, you can sort of see how they went about sort of generating the prompts to ask the questions, as well as some of the outputs from the answers. So again, I won't go into detail here, but I will pause for a second because I think the level of detail that you can get from this it can be pretty significant if trained properly. Although there's, as I will mention in a moment, there are challenges with element errors that are always possible. And so, another big area, so that's an area around adverse event extraction. Another important area is around probabilistic computable phenotyping. And so when we talk about that, and I think Rishi for this and a few other slides, essentially we're trying to accurately identify a health condition of interest from healthcare data that uses a combination of codes, uses a proxy essentially in order to say that a patient has diabetes based on a number of features that themselves aren't are predictive of the feature, or can sometimes be deterministic of it, but are not always. And so for many conditions, it may not be 100% or 0% that you have a certain condition. You need to actually assign a probability of that condition on the basis of a number of set of features. And so you can imagine that you have a variety of gold standard, silver standard, and even bronze standard applications in your healthcare system. Like if you have acute kidney injury or chronic kidney disease and you get a kidney biopsy, that's a gold standard. You have basically a deterministic underlying pathophysiologic assessment and determination of the disease process. But in many cases in electronic health record data, you have a variety of lab tests and other sorts of tests that are suggestive but not deterministic for an outcome, for a phenotype. And so the Sentinel Innovation Center has been engaged for the last 5 years in evaluating a variety of different methods and tools to extract electronic health record information to conduct probabilistic phenotyping. The opportunity space here is many of these have been using sort of the the state-of-the-art natural language processing right prior to essentially the explosion of the large language models onto the scene. And so there's an opportunity to sort of take the lessons learned and the work done here that has been very successful in and evaluate and try to understand where the large language models might also have a highly successful phenotype prediction and execution. And so, sort of to give everyone a frame, like a lot of the NLP high throughput phenotyping algorithms essentially use a natural language processing solution that reviews a document. It assesses the ICD-9s and 10 codes and CPT codes and other sorts of things, SNOMED codes, assigns them for the document, and then it uses those codes along with structured data codes to assess the likelihood of a phenotype and then to validate it using a chart review or other sorts of processes. And you can imagine with large language, it's outputting free text narration. And so translating large language models from a free text output to essentially coded lists can be challenging, as you'll see in a moment. And so this is a group that basically evaluated large language models for the utility of EHR phenotyping. And this was a group here at Vanderbilt. Essentially, they took a slightly different approach. So what they did was they evaluated a couple different large language models, but they said, okay, we would like to see how well a large language model can actually develop a SQL query that could be run in order to assess a phenotype of a patient using a standard sort of structured database. How well can it do? And so what they did is they had a series of prompts and questions. The LLMs would basically generate the analytic code, and then experts would evaluate the code, assess it for how well it did, actually correct it, run it on the databases, and then compare it to some clinically validated algorithms from the eMERGE clinical network. And so I think what shows on the bottom is for sort of diabetes, for dementia, and hypothyroidism is that there was a large gap in the performance of GPT 3.5 to GPT 4, and that while the overall sort of positive predictive value and negative predictive value were similar or slightly inferior to the manually curated phenotypes that were previously published, I think one of the big things that they learned is that they still had to do a fair degree of sort of manual curation and manual adaptation to these algorithms. So like leveraging these algorithms to basically create an automated phenotype algorithm and then deploy that at scale isn't yet prime time. It still requires a series of sort of adjustment and updating steps in order to be able to execute them, but does show promise for long-term use, particularly in the GPT-4 family. So this is another sort of opportunity space for LLMs. It's sort of a clinical text summarization. And you could visualize this a couple different ways. You could visualize this as a summarization for a provider, summarization for a patient. You could have it summarized for a public health official or an FDA official looking to sort of assess a body of documents for possibilities of adverse events or certain sort of issues. And what this actually showed, this was a really interesting study that basically they allowed providers to sort of summarize a set of clinical data. They allowed the LLM to summarize the clinical data, and then they basically had reviewers assess, blinded to which, whether the LLM did it or the human did the summary, on completeness, correctness, and conciseness. And what that study found was that even though conciseness and correctness was relatively balanced between the human and the LLM, the completeness, the sort of the verbosity of the report and sort of the thoroughness was actually more comprehensive in the LLM versus the human generated report. And so, but what about the challenges? I've sort of sprinkled those in a little bit because it's hard to talk about this without some of the challenges, but I think there's sort of some key issues that need to be addressed in order to be able to sort of use these technologies effectively. And the first one is prompt engineering itself. So what you've heard is that, you type in the text, and I'm sure almost everyone on the call has played with GPT as well. You put in a question and it starts generating a text again, miraculously enough, just sort of using the prompt and then starting to put sort of response words after that, and then just stacking them until it gets a full response. But how you do that is a new domain, new and complex domain in and of itself. There was a recent review that hasn't been published, but is in ArXiv, essentially looking at all of the different flavors of prompt engineering and all of the different sort of research that's going on to try to actually optimize the prompts for given purposes, for sort of reasoning and logic, for reducing hallucinations, for sort of task analysis, for and so it's sort of interesting in and of itself that the LLM as a new technology, because it requires prompts in order to be able to extract information, has sort of generated a whole new domain of research around that. And I think in product surveillance, it's going to be really important because you're going to have to really develop prompts that sort of help you with sort of temporal relationships with exposures, to help you with sort of being highly specific in terms of the information extracted, in terms of like no hives prior to today, or or issues around sort of, if you basically use retrieval augmented generation and you ask like, well, did this patient ever have a rash? Sort of tuning of these prompts is a key performance issue for success in the future. I think another key issue is causal inference, and so one of the things that the FDA and Sentinel is really interested in, of course, is causal inference and causal reasoning, and LLMs have had some problems in that regard. So this is a study that they just recently did. Again, much of this is preprint because the field is so new, but essentially they would take cards, take information that said, you have to have this for this to be true, or you basically have causation sort of sequences. And what it would do is it would sort of ask the LLM, if you know the decedent piece of the rule, can it actually tell you what is required in order to achieve that particular content? And it found significant gaps across a couple of different sort of inferencing tests that the LLM was unable to adequately predict. Another issue that's really relevant to medical information and electronic health record data is protected health information leakage. And so even though a lot of this is being addressed, it's an area of active research, there are essentially issues with adversarial attacks and PI leakage, where you can basically ask prompts in certain ways, and the LLM will generate results that are exposing information that it should not. And so you have this sort of ongoing war, for lack of a better word, where the LLM creators are sort of continually doing reinforcement learning to try to extinguish the behaviors and the gaps, and then you have sort of different groups and different individuals that are basically assessing these. I mean, I think these will be a little bit safer if you deploy them in a healthcare system and you encapsulate it inside of a healthcare environment, or you only use it in sort of in environments where there's business associated agreements and sort of rules of behavior. But I mean, these are issues that have to be addressed when you're leveraging LLMs for any use case. And so I looked for a medical product example and didn't find one, but no discussion of large language models is complete without a discussion around hallucinations. And so, here's a good clinical example in a publication where essentially they asked the LLM, they gave it a vignette where they asked for a 24-year-old pregnant woman at 28-week gestation, coming with fever and chills and pain in her joints, essentially, asking the LLM basically, oh, it looks like that this is possibly Lyme disease, or it looks like this is Lyme disease. What medication would you use to treat this? And what they found was that the GPT 3.5 would recommend tetracycline, and the physician would recommend amoxicillin. The key piece of information here is that tetracycline is contraindicated in a pregnant patient, and so that inference piece was missed, even though the overall explanation that is in the fine print there sort of went through a lot of information that was relevant, but missed sort of a key piece of information. And so depending on the use case, that level of error may be perfectly fine. If you're looking at the population level at sort of large scale analytics, and a 5 or 10% error rate is acceptable for hypothesis discovery and some signals. But in the situations where it's not, then buyer beware. I think the other challenge we have with LLMs is a continuous learning environment. So these machine learning algorithms are being updated with new textual information constantly. And so what you see here is essentially a study that was done last year looking at ChatGPT 3.5 and 4. They basically asked the set of prompts in March of 23, and then they asked the same set of prompts in June of 23, and then they manually assessed them for accuracy. And you can see that essentially some questions got more accurate, some questions got less accurate, and some stayed the same. But this means that if you're trying to build a stable sort of system and you validate it against a reference standard that's sort of for the use case that you need it for, and you're using an online algorithm that's sort of updated without you sort of knowing when and where that's being done, performance could improve, degrade, either way. And so careful vigilance and sort of evaluation of these algorithms over time, or the use of an algorithm that's not changing. So you could actually have an open source LLM that's static, trained at a given point, and then you fine tune it, or you sort of apply it that for your tailored use case. And that also would sort of be a way to sort of get around this. But of course you miss the benefits of potential new information that would be in the training sample. And so the last thing that I want to say is we've got a really long way to go. I know that it seems like there are 1,000 articles in the literature on large language models, but this was a presentation that Nigam Shah gave a few weeks ago at our institution, and he hasn't yet had a chance to publish this, but he did allow me to use it explicitly. And they basically did a large systematic review of the literature looking at sort of LLMs and what's being done to evaluate and assess and validate these things. And most of the literature right now is in medical education, in diagnostics, and in patient education. If you look down into sort of more around sort of extraction of information, sort of clinical information, text, you've got a much smaller set of publications, and there's a huge opportunity for additional work in this area in post-market surveillance. And so in conclusion, they're an amazing new technology, but they're not magic, and there are plenty of problems that need to be addressed. That being said, I think there are key opportunities in medical product safety surveillance to do adverse event detection, probabilistic phenotyping, and information synthesis, while also opportunities in addressing a variety of challenges such as lack of evaluation in this space, complexities of prompt engineering, mitigation of hallucinations, and then evolving model performance over time. And so I intended for about 15 minutes to be able to sort of answer questions from the audience, and I think I about hit it. So happy to answer questions.
Great, Michael. Thank you. This was a really fantastic overview of the challenges and opportunities of LLM. So with that, this floor is open for questions now. As a reminder, your lines are muted. So if you want to pose a question, please type them in the Q&A box, and we will read them out for you. Okay, very good. So I think as people are thinking about this, there is a request, Michael, for showing the summary slide again. So if you can just...
Oh, yeah, absolutely. You mean the key conclusions?
Yeah, I think it's this one, yes. So I can start with a question as people are thinking about their own questions, Michael. So there was a discussion in your slide deck earlier on about kind of the key differentiation between some models that are widely used, which are more general purpose, versus those that are trained more on EHR data. And so my question to you, Michael, is that how frequently do you think in as we move forward with this, do you think we are going to have to train them for specific applications, or do you think we will be able to take the models that are, or LLMs that are developed on some healthcare system and really plug in to other healthcare systems in terms of their transportability? So I don't know if you have thought about this, or what are some of the pros and cons of training or fine-tuning your own versus taking something that already exists and plug it in?
Yeah, that's a good question and sort of goes to the heart of the whole discussion. I think it's a little too early to know. I mean, I think there's research going into what's the right. So one of the questions is what's the right data to feed the large language model to get it to perform out of the box as efficiently as it can with a minimum of hallucinations and the maximum of sort of relevant information generation. And so that question is just train it with everything from the kitchen sink from publicly available data versus train it with a highly curated set of data from the electronic health record, or maybe you train it with medical textbooks and all the medical school learning and the electronic health record. So I think the jury is sort of still out on that. I think we've seen some instances where some use cases, the medically trained LLMs are able to sort of achieve better performance for specific use cases. I think it's not entirely known how if you build a University of Florida LLM and you go to Mass General Brigham, and you deploy it there, what you're going to get. Some of the challenges in even doing that right now are the PHI leakage makes it so that where everybody's a little skittish, to sort of do that without a lot of sort of protections in place. But those questions I think are relevant and will be answered, by research and different things. And then you've got the other side, right? So if it's a black box, you've got the inputs that you can evaluate for appropriateness or for performance, and then you can evaluate all the outputs, which are the prompt engineering and then sort of taking labeled data and fine tuning it. And so I think there's a lot of work going on, and I think a lot of the early work that's relevant to medical product safety will be sort of doing fine tuning of more general purpose LLMs that allow us to sort of update the accuracy for specific applications in safety detection, and then validate them, and then use them for that purpose.
Yeah, great. Thanks, Michael. So we have a bunch of questions trickling in. So Robert Davis has a question about causality from a machine learning perspective, and how is this similar or dissimilar from epidemiologic consideration of causality?
That's a good question. So LLMs don't really have a framework for inference. It reminds me of sort of a lot of the sort of machine learning where you have sort of explicit relationships, and, you sort of have causal pathways, and then you have, mediators and confounders. And so the LLMs just don't have any of that sort of framework built into them. They're essentially just a large sort of mathematical vector of frequency and sort of ordering and composition of words, and then it just you ask sort of thing, and then it sort of generates from that sort of probability at a sort of a scale that we can't comprehend. And so sometimes it'll be right and sometimes it'll be wrong. But I think if we're going to sort of use it for causal inference, it's probably something else that will be built downstream or upstream that will sort of then it will be used to assist. But right now, I think it has challenges in sort of being directly used for causal inference.
Yeah, absolutely. So there was one comment from Sandra Rodriguez that generative AI is still a new technology, so skill gap is it will continue to be a challenge, which is absolutely true. As Michael presented, most of these papers are not even out in full publication form, so we are all learning. So a question from David Carell: can you speculate about how and when it may be possible to healthcare institutions to create their own LLMs and encapsulate it inside their own environment and secure spaces? And is there a way for institutions to share the training data securely?
Yeah, that's a great question. Thank you, David. Well, I mean, I think so. Some of that is sort of infrastructure and cost. So I think one of the reasons why you see some institutions sort of out and having these LLMs already is because of sort of large grants and large sort of institutional investment sort of early in the game. I think a lot of institutions could build a smaller LLM, but once you get up to sort of large scale, like you saw on that one slide that I presented with billions of parameters, it's actually cost prohibitive for single institutions to do that and then keep it up to date. So I think there's this tension, right, where the BERT models and some of the older, smaller technologies, transformer technology and stuff, may be fine for certain applications, and there may be certain other applications that only the large, sort of truly sort of enterprise scale LLMs may be able to be appropriately used for. But I don't know exactly how feasible it's going to be for every healthcare institution to have its own LLM. I think certainly that's not going to be the case.
Yeah, thanks, Michael. There is a question that is posted anonymously saying popular LLMs suffer from a lack of reproducibility when they are up-versioned. Updates to improve model performance in one area can have unintended consequences in other areas. And so any thoughts on how this challenge can be addressed, or any general thoughts on reliability of LLMs as they evolve?
Yeah, that's a good question. I Yeah, I think that's hard. I think most of the work right now is going into providing evaluation, validation, and safety harnesses on the outputs. Like, so until we have a fundamental sort of breakthrough in understanding exactly how everything is happening underneath, such that that understanding will allow us to sort of change some of the emergent properties of the technology. Most of the work at sort of reproducibility and stability over time is going into catching things as they come out. And then I've seen some innovative pieces that basically like assess the LLM outputs, look for errors, and then feed back the errors to the LLM and say, hey, you made this error, fix it. And then it fixes it. And then, so you have all this like the framework of multiple sort of units working together to sort of come to create a final product that's relatively error-free. But yeah, it's wide open innovation space right now.
Yeah, thanks, Michael. So there's one more question from Avik Ray. How can we increase transparency on how LLMs make clinical decisions, given that we really don't know what they attribute their results to? Do you think prompt engineering, like asking questions to the LLM, how the decision was arrived at, would be something that could be useful?
Yeah, that's a tough question. And I feel like the bar is relatively high there if you're dealing with direct patient care, because there's been recent literature also that has shown that there's an algorithmic reliance bias. So there's a really cool publication last year that showed that it gave clinicians sort of a LLM guidance, and then asked them what they would do, but and it gave it good guidance, and then they basically broke the guidance and made it terrible, made it wrong, and then gave the clinicians the guidance, and it actually improved the clinician answers in the good guidance by 4% and decreased the performance by 11% if the clinicians were given inappropriate or wrong guidance, which is really scary when you think about that from a cognitive perspective. And so I feel like that's a high bar. But yeah, sorry, I may have lost track of part of that question, but yeah, sorry if I need to.
No, these are all kind of thought exercises in many ways, right? Because most of us don't have a firm handle on things as they are developing. So thank you.
I don't either.
Yeah. There's one more question from an anonymous attendee. Do you recommend a static LLM model without fine tuning so results are consistent, or would you go with a continuous fine tuning of models, which could change results over time and may revert progress in some cases, because each step is requiring human intervention for validation. So it's a balance that you need to strike there. So what would be your recommendation, Michael?
Yeah, so this is my own personal preference opinion, but right now I feel like using the best of breed sort of open source LLM that can be static, and brought into your environment wherever you are, and then fine tuned for a use case, probably is going to be the most stable sort of pipeline for a lot of things that we would like to do. right now the sort of large open source LLMs are not that much inferior to they're not so inferior to the large sort of publicly online models like ChatGPT that they're not usable. And so with fine tuning, you can sort of really tailor it to the task that you're interested in. And so that, I mean, that's my own, but that's totally my personal preference at the moment.
Okay, great. So I think there is one more question that's coming in, which is something that you mentioned. So Jay Yang is wondering if so LLMs rely on large number of computational environment and GPU resources. If we apply them on large cohorts, you have deployment challenges compared to classical NLP models. So what's your opinion in terms of trade-off that you have between the speed and GPU resources that's needed versus the accuracy that LLMs can possibly bring about?
Yeah. Yeah, there's no question it's night and day on computational requirements. I don't know. I mean, I think we're still seeing instances where sort of what you would, and I don't like the term sort of old school, the maybe traditional NLP where you have a machine learning stack, you have sort of breaks things down into tokens and then sort of assesses them in phrases and assigns sort of tokens. Assigns sort of medical vocabulary assignments from SNOMED or other things to them. I mean, there are situations where those do quite well. And are deployable and portable and usable. And so I don't think it's an or. I don't think LLMs are going to like saturate the environment and that's all we're going to use. I think there's sort of going to be like a spectrum of applications for a variety of different use cases. I mean, if you really need high validity and you have a very narrow focus and you have computational sort of constrictions, those sorts of LLM technologies still can be very successal at achieving the end. It's just they may not be as sort of generalizable as some of the other things. So I still use them myself.
Yeah, no, absolutely. And sorry, Michael, there's just a lot of interest in this, looks like. So there's one more question that just came in. If not LLMs, what's the best AI tool do you think is going to be most applicable to safety surveillance that's accurate and more easily trained?
I mean, I don't think there is one. I don't think there is a tool that is easy.
Right.
All of it, it's more like all of it requires. I mean, the bigger challenge for me is that it's not very democratized right now. The use of machine learning and AI technologies require a high degree of sort of multidisciplinary skill sets to apply to to any use case that you want to use it. Hopefully over the next couple of years, the barriers and to that will decline as we know more. But I think that I don't think there is an easier not right now.
Yeah, one size fits all solution I think doesn't exist. Okay, very good. Thank you. There's one more question rolling in as we try to wrap up. Would FDA accept future applications that solely rely on LLMs for safety, for signal identification evaluation, or are we far from it? I don't know, Michael, if you have thoughts, but I think that day is not any closer than we might want to. But
so I do not in any way speak for the FDA, nor should my comments be construed as such. I'm my own sort of academic individual, but I would say, the FDA has been really sort of careful, rigorous about how it sort of evaluates any set of evidence during a pursuit of pre-market review or post-market application. And I would expect that they would require a similar degree of rigor, regardless of the underlying technology that is applied for any particular evaluation.
Yep, and I think with technologies like LLM, it is even more challenging because of the black box nature of the outputs that are generated. And so you have to be extra careful there, and I'm sure FDA is thinking about this carefully as well. So I think that are all the questions, Mike. I really wanted to appreciate your time today, and thank you for a really wonderful presentation. As you saw from the participation, this was a popular topic. So thanks again to you, and thanks everybody for joining and sending in your questions. As a quick reminder, the slides as well as the presentation will be both made available on our website, sentinelinitiative.org. So you can find it there and share if you like. So thank you. We will see you around next time.